21 ECE 2 and 2T Control Systems Theory and Applications Unit 4 Part 1 Frequency Domain Analysis. In this unit we are going to see how can we apply the frequency domain analysis for control systems. For this purpose, first we are going to see the sinusoidal transfer function and sinusoidal response. Sinusoidal response is the output of the system when a sinusoidal input is applied. The frequency domain transfer function is a sinusoidal transfer function T of j omega, which represents the ratio of the system's sinusoidal response to the sinusoidal input in the frequency domain. It is also referred to as the frequency domain transfer function. Next we are going to see the steps to derive T of j omega, that is sinusoidal transfer function. First step is to develop a physical model using the system's basic elements or parameters. Write the governing differential equation for the system. Apply the Laplace transform to the differential equation to convert it into S-domain. Derive the S-domain transfer function as the ratio of output to input. Next, replace S with j omega to obtain the frequency domain transfer function T of j omega. In this way, we can obtain the sinusoidal transfer function for a system. When a linear time invariant system is driven by a sinusoidal input of frequency omega, the output will also be a sinusoidal signal with the same frequency. Next, we are going to see the effect on the amplitude and phase. The system modifies the input signal's amplitude and phase based on the transfer function T of j omega. The output amplitude is the product of the input amplitude and the magnitude of T of j omega. The output phase is the sum of the input phase and the phase angle of T of j omega. Next we are going to see the sinusoidal transfer function mathematically. Let T of j omega is equal to modulus of T of j omega, that is magnitude of T of j omega, angle T of j omega. So we are separating the overall T of j omega, that is sinusoidal transfer function, in terms of magnitude and phase. Here modulus of T of j omega is the magnitude of T of j omega and angle T of j omega is the phase of T of j omega. Let's take R of t is equal to A sin omega t plus theta, which is represented by A angle theta. Now let's calculate the response C of t, which is equal to R of t into T of j omega. So here R of t is A angle theta and T of j omega is magnitude T j omega angle T of j omega, which is equal to A into magnitude of T of j omega angle theta plus angle T of j omega, which can be represented as B angle phi. Here B is the magnitude of response and phi is the phase of the response, which can be calculated by B is equal to A into magnitude of T of j omega and phi is equal to theta plus angle T of j omega. The system with sinusoidal transfer function can be represented as shown in the figure. Next, frequency response. The frequency domain transfer function T of j omega is a complex function dependent on omega, representing how the response changes with different frequencies. It has two parts, magnitude and phase. So here T of j omega and angle T of j omega are real valued functions of omega and collectively forms the system's frequency response. Here open loop and closed loop systems, the frequency response can be analyzed both open loop and closed loop systems by substituting S equal to j omega in the transfer function. Next, we are going to see main frequency domain specifications. The first one is gain margin, that is Kg. Gain margin is the additional gain required to bring a system to the verge of instability. The gain margin can be determined as the reciprocal of the magnitude of open loop transfer function at the phase crossover frequency. The phase crossover frequency is the frequency where the phase of the open loop transfer function is equal to 180 degree. The gain margin in decibel can be expressed as Kg is equal to 20 log Kg. So here Kg is 20 log 1 by magnitude of G of j omega at Pc. Pc is the phase crossover frequency. The gain margin is the negative of dB magnitude of G of j omega at phase crossover frequency. So the gain margin indicates the extra gain the system can handle before becoming unstable. Next is phase margin. Phase margin represents the additional phase lag required at the gain crossover frequency to make the system unstable. The gain crossover frequency is where the magnitude of open loop transfer function is 1 or 0 dB. The phase margin is calculated by adding 180 degree to the phase angle of the system at this frequency. So here phase margin is given as 180 plus 5 GC. GC is the gain crossover frequency. These metrics provide a clear understanding of how far the system is from instability in terms of both gain and phase. Next we are going to see how we can analyze the frequency response. There are mainly two ways to analyze the frequency response. Those are analytically and graphically. In analytical method, we use mathematical equations and computations to derive the frequency response. In this unit, we are going to see how to analyze the frequency response graphically. So several graphical methods are used to visually analyze the response, including Bode plot, polar plot, Nichols plot, Nichols chart, MNC circles, and these methods help in understanding the system behavior across different frequencies with both precision and visual clarity. In this unit, we are going to see the Bode plot and polar plot for frequency response analysis. Bode plot is a visual tool used to represent the system's frequency response. It mainly consists of magnitude plot and phase plot. The magnitude plot displays the system's gain in decibels versus frequency on the logarithmic scale. The Bode plot plots on the semi-log graph sheet. So we represent the frequency in the logarithmic scale and the gain in the decibels. Phase plot shows the phase shift introduced by the system in degrees plotted against frequency. The key applications of Bode plot are to analyze the stability and performance of control systems and to help in understanding the frequency characteristics of filters and dynamic systems. This makes the Bode plot an essential tool in frequency response analysis. Next, we are going to see an example problem on Bode plot. Sketch the Bode plot for the following transfer function. Here the transfer function is given as h of s equal to s square by 1 plus 0.2 s into 1 plus 0.02 s. The first step to plot the Bode plot is to write the given transfer function in frequency domain. To represent the given transfer function in frequency domain, we need to replace s is equal to j omega. So let's rewrite the equation given in the question. So the transfer function in frequency domain can be written as g of j omega is equal to j omega the whole square divided by 1 plus j into 0.2 omega into 1 plus j into 0.02 omega. In the Bode plot, we have two plots to plot on the graph sheet. Those are magnitude plot and phase plot. First we are going to see how to do the magnitude plot. So from the given frequency domain transfer function, first step is to determine the corner frequencies. So we can find out two corner frequencies from this given transfer function, which are omega c1 and omega c2. Omega c1 is 1 by 0.2, which is equal to 5 radian per second, and omega c2 is 1 by 0.02, which is equal to 50 radian per second. So next we are going to see which are the different terms in the frequency domain transfer function. So the different terms are j omega the whole square, 1 by 1 plus j omega 0.2 and 1 by 1 plus j 0.02 omega. Next we are going to construct a table to plot the magnitude plot. So this table consists of 4 columns: term, corner frequency in radian per second, slope, that is the unit is dB per decade, and change in slope dB per decade. So the terms can be found out from the given frequency domain transfer function. So the terms are j omega the whole square, 1 by 1 plus j into 0.2 omega and 1 by 1 plus j into 0.02 omega. Next we are going to see each corner frequency against each term. So for j omega the whole square there is no corner frequency, and the slope for j omega the whole square, the slope is plus 40. The term is in the numerator and it is the square of the j omega. So our slope will be plus 40. Next term is 1 by 1 plus 0.2 j omega. So the omega c1 corner frequency is 1 by 0.2, that is equal to 5 radian per second, and the term is in the denominator with first degree. So the slope is minus 20. So the total slope will be 40 minus 20, that is equal to 20. Next term is 1 by 1 plus j 0.02 omega. So the omega c2 is corner frequency is 1 by 0.02, which is equal to 50 radian per second. Again the slope is minus 20. So the total slope is, change in slope is 20 plus minus 20, which is equal to 0. So next we need to choose two more frequencies. Those are omega L, which is less than omega C1, and omega H, which is greater than omega C2. Let's take omega L equal to 0.5 radian per second, which is lesser than 5 radian per second, that is omega C1, and omega H is equal to 100 radian per second, which is greater than 50 radian per second, that is omega C2. So next we are going to calculate the gain for different frequencies. Here we have taken the frequencies omega equal to omega L, omega equal to omega C1, omega C2 and omega H. At omega equal to omega L, we can calculate the gain A is equal to 20 log j omega the whole square, magnitude of j omega the whole square, which is equal to 20 log omega square, which is equal to 20 log 0.5 the square, is equal to minus 12 dB. And at omega equal to omega c1 also we can calculate the gain as A is equal to 20 log magnitude of j omega square, which is equal to 20 log 5 square, which is equal to 28 dB. At omega equal to omega c2, the gain can be calculated with the equation slope from omega c1 to omega c2 into log omega c2 by omega c1 plus magnitude at omega equal to omega c1. So here 20 into log 50 by 5 plus 28, which is equal to 48 dB. At omega equal to omega h, the magnitude is equal to slope from omega c2 to omega h into log omega h by omega c2 plus magnitude at omega equal to omega c2. So here slope from omega C2 to omega h is 0. Then log 100 by 50 plus 48, which is equal to 48 dB. Now we have got different magnitude values for different frequencies. So mark each corresponding magnitude in the semi-log graph sheet corresponding to each frequency of omega L, omega C1, omega C2 and omega H. So here we can take the x-axis as frequency and y-axis as magnitude in dB and mark all the points and connect them to get the magnitude plot. Next we are going to see the phase plot. So to plot the phase, first we need to determine the phase angle as a function of omega for the given transfer function. So for the given transfer function, we have a j omega the whole square term in the numerator. So the angle is 180 degree for that term alone. Then for the denominator terms, we can determine the angle by tan inverse 0.2 omega and tan inverse 0.02 omega. So here the overall angle for the given transfer function can be written as 180 degree minus tan inverse 0.2 omega plus tan inverse 0.02 omega. So from this equation, by substituting the different omega values, we can get the different phase angle values as shown in the table. We have taken omega as 0.5, 1, 5, 10, 25, 50, 75 and 100, and we have calculated the corresponding phase values. After calculating this, we can plot the phase plot also in the semi-log graph sheet. So in the x-axis we can take the frequencies and in the y-axis we can mark the magnitude and phase of the transfer function. We can mark each corresponding magnitude and phase and we can connect the plot. And in this way we can plot the Bode plot. These are the references used for the materials. Thank you.